All right. Hi. Okay, so I'm going to give you a second to quieten down. All right. So I'm going to talk today about arrows. Arrows are an abstraction for effectful computations, and they're particularly useful for representing computation graphs. So by that I mean, the computation made up of components that are kind of connected together by dependencies, where the structure of those dependencies, in particular where the structure of those dependencies doesn't really change. So monads are also an abstraction for representing effectful computations. But with a monad, monads always support dynamic dependencies, so the structure of the graph can change based on earlier effectful operations. And you don't always want that. Sometimes you want the guarantee that the structure of the thing remains kind of static, and so for that, arrows are a suitable choice. And they've been used for parsers, for functional reactive programming, incremental computation. At Jane Street, we use them for a library called Bonsai, which is our kind of web framework. So arrows are quite nice. The problem they have their interface is like somewhat unpleasant to use. There are some kind of you can add special syntax to try and make it nicer and things, but it's fundamentally they're a little awkward to use. And so this talk is really about an alternative API to arrows that is nicer to use. Right, so first, arrows. So here is some camel syntax for the interface for an arrow. So an arrow is a type kind of alpha, beta, t. That represents a computation that takes an alpha and kind of produces a beta. And we can lift a pure function into an arrow with the R combinator. We can compose these computations together sequentially, one after the other. And also you've got the kind of first and second. So what these do is they let you, if you have like an alpha-beta computation, alpha to beta computation, you can kind of turn that into an alpha cross gamma to beta cross gamma computation. So there's you can run the computation on part of the input to produce part of the output. And second is kind of doing the same thing, but on the other side. I also think it's important to include, so these three, you can implement these with just R, but it's actually quite important to have them as primitives in the specification, really, because that makes sure that all the dependencies in your graph are visible to the implementation of the arrow, which is important for performance and things. Right, yes. So our example, our running example in this talk is going to be a kind of a toy incremental computation library. And so what do I mean by that? Basically, this is going to let you you're going to define a computation that reads some references, some mutable references, and defines some outputs that are just kind of side-effecting outputs. And you're going to be able to compile that into a function that's kind of unit to unit, which runs the computation. And then when you call that function the second time, it's only going to perform the parts of the computation graph that where the inputs they depended on have changed since the last time you called it. That's what I meant by incremental. You only rerun the stuff that's changed. And so our interface for that, we've got two operations, input and output. So input, you take a ref and an equality function, so you can tell when the reference has changed, and that gives you a computation that's kind of unit to alpha. And output, you could take an impure function, alpha to unit, that kind of does some side effect, and you turn that into a computation alpha to unit. And then compile is the way that we kind of turn one of these expressions into, one of these terms into an actual function. So it takes a unit to unit t and gives you a unit to unit function. And we can try and use this like this. So here's a simple graph. It's taking in two references, A and B, and then it's using them as inputs and building some kind of graph based on them. It's pretty hard to read off of this code, the structure of the graph. This is essentially the point of the talk, is that this is very hard to read. This is how our Bonsai code did look at one point. It was understandably difficult to persuade developers at Jane Street that this is how they should write web programs. And so we tried to make something else. Right, so this is the graph that it is in fact producing. So it's a relatively simple graph. You kind of got two inputs, A and B. There's a computation node that's timesing A by 10. There's one that adds 5 to that. One that times B by 3.5, and then one that takes that computation and the B and makes a string out of it. And then we got these outputs at the bottom that just print them. Yes, and so what else could we do? Applicatives. Applicatives are another abstraction for representing computations with effects. And they also, like arrows, they don't support dynamic dependency. They have that nice static graph structure. So that's good. So what happens if we try and implement our library with an applicative? Okay. All right, so here's the API. Oh, well, here's my preferred API for applicatives. This is not the standard one, although it is in the original applicatives paper. It's called the monoidal interface in that one. But I think it's slightly nicer. It gets at the heart of what applicative is doing a little more directly. So you have an alpha t. Right, so this time we have just an alpha t. This represents a computation that's going to return an alpha. And we can use a map function to generate a new graph node, a new computation b that returns a beta that by applying the function to the node computation that you gave it as input. You can also use pure to create like just a constant returning computation, and both. You can combine two computations together as well. Oh, I meant to take that slide out. Okay, ignore that slide. Right. Right, and so there's an obvious difference between arrows and applicatives. So with an arrow, when you've got when you're trying to have a computation that takes a bunch of alphas and produces a beta, you kind of represent that with like a product of alphas to beta t. Whereas with an applicative, you would represent the same thing by alpha t, blah, 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 to beta t. And really the key thing is that because you're using the normal function arrow here, you're able to use the binding constructs of your normal, like your meta language to represent how you compose things. And this makes things much nicer. Whereas when you're using the product, you end up essentially, you're basically just doing the structural rules yourself manually by hand, right? You're doing like exchange and weakening and contraction on a big product that's your context. You're not allowed to use the facilities for manipulating a context that your language already has.
Could you uncurry this?
Could I uncurry the applicative one?
Could we have product of A's?
Yes. No. Yes, you could. I think that would be unusual. Yeah. Yeah. It's just kind of worse, so people don't tend to do it that way. All right. Anyway, let's try making our incremental library with this applicative. So here's input and output and compile. Their types have changed slightly because of the slightly different approach. So now input returns an alpha t, and output takes an alpha t and gives you a unit t, and compile just takes a unit t to produce the thing. And we can use that to produce our example. And this already looks better than the last one. We've now been able to give names to some of the subcomponents of the graph, so that seems pretty good. And in fact, in modern ACaml, you can use, there's a nice feature of binding operators. So I can define a let that is map and an and that is both and use that. So this is designed for applicatives and monads. And with that representation, you get this, it's kind of slightly even more, it's even clearer. You're built like the C component, you're building it by like binding A to X and then X times 10. And in fact, very recent ACamls have support for punning. So if you do like let X equals X in, it's the same as let. You can just write that as let X in. So you kind of get us down to this, which is now a pretty direct encoding of the graph that you're trying to represent. So you've just got like C is, it depends on A and it's A times 10. And E here is it depends on C and B and it's this expression using C and B. So that seems pretty good. The problem is that we actually didn't make the graph we meant to. We made this graph instead. We lost all the sharing because applicatives can't actually represent sharing. Applicatives don't represent an arbitrary computation graph. They represent an arbitrary computation tree. It looks like we had sharing. So if I go back, no, point that way. Right. You like C there. We defined C as this thing that's made out of A, and then we used it in two places. And so it looks like there's sharing there, but the sharing is just at the meta language level. There's no actual sharing under. Really, the C there represents the whole computation graph, and we've just put it in. We've just copied it twice into two places. Yes. Right. So, I think one key. So the key point of this is that it is a reasonable way to think about arrows is that they are applicatives with sharing. That's what's going on there. And the problems with their interface are mostly due to the fact they're kind of fundamental in trying to use an algebraic approach to represent sharing. Like algebra is great at trees, it is not great at graphs. And so that's what's causing all of that. You end up, anything like that, you always end up manipulating a context manually. But there are non-algebraic approaches to representing sharing. There are other things that represent sharing more naturally. In particular, heaps also describe sharing. So by a heap, I mean like a mutable store, so with references that you can generate fresh references and compare them for equality. These are all about sharing. The whole point of a mutable heap is about like which pieces of state are aliased with which other pieces of state. So for example, here is some Haskell code using the ST monad, which is a monad for a kind of a mutable heap. And this code creates essentially references with the exact same graph structure as our intended graph. In particular, the C that you can get by reading E or D is the same C, and if you use the equality function on stref, you will see that it is in fact the same C, and so it has an account of the sharing in it. Right, so here's the ST monad interface in Haskell. To make everything more consistent with the rest of the talk, I'm going to swap it to a camel. Why is it off screen? It wasn't off screen on my laptop. That's weird. Okay, well, we just lost some syntax. We didn't lose anything important. Right. Okay, so so you've got two types here. You've got st.t and ref.t. So the st.t is representing a computation that produces an A whilst manipulating references on the heap K. So K is called a thread parameter in the ST monad, like documentation and things. But I think you should think of it as being indexed by the heap that is being manipulated. So this is a computation that manipulates references on the heap K, and the reference and the ref.t is a reference holding an alpha that is on the heap K. And st just forms a monad. It's got return and bind. And ref, you've got create, which lets you create a new reference. And importantly, create is in st, like for the appropriate heap. And you've got equality. You can compare two references for equality. And this is enough of the st interface to kind of create things with sharing and detect the sharing. So taking this as our inspiration, we can now define a new API for arrows. So here is we're going to have a monad called I'm calling the builder monad. So it kind of has, and this represents a computation returning an alpha whilst manipulating graph nodes in the computation graph K. And again, it forms a monad. And then we have node, which represents a node in the computation graph. So it's a node that computes an alpha whilst in the computation graph K. And its interface is actually almost just an applicative, right? So you've got pure in both and first and second, exactly as they would be if it was an applicative. And then the only difference is map. The return of map is in the builder.t monad. Because when you use map to create a new node from an old node, you have this existing node and a function. You're going to make a new node that represents running this function on that node. Doing that creates a new node, and so it lives inside the builder.t monad. And modulo that difference, this is just the applicative interface. I've been ignoring laws in the discussion so far. It has the same laws as the applicative, just slightly adjusted because there's a monad. Right, and so we can use that. There we go. Oh, right, yeah. So now, compared to our previous two approaches, we now still have this feature that the usual arrow is how we're combining computations into taking a bunch of input computations, producing an output, but the output now lives in this builder.t monad, unlike in the applicative version. And we can make our incremental library using this as well. So now input returns you a fresh node, and it's in builder.t because it's building a new node, and output is building a node, but it actually doesn't even have to give you the node because no one really wants a unit node anyway, so it just returns unit now. And compile takes a unit k builder.t. It's polymorphic, just like it's the same as run st for the st monad. It's the same thing. So if someone gives you a builder.t that works for kind of any heap, you can use that to construct a unit-to-unit function. It does the right thing. And now this is our original computation written directly using this interface. And it's already an improvement. It's a little hard to read. It's kind of CPS style. But you can see we did at least get to name all the components of the graph, A, B, C, D, and so forth. And we get the right sharing, unlike the applicative interface. If we again take advantage of the binding operators, so I'm going to use let, star, and return. Those are the builder monad, basically. And then let, ampersand, and ampersand, that's the node applicative. So ampersand's the node, and star is builder. So we do that, then it becomes this, again, using the punning. So you get to write it. And this is a pretty direct representation of the graph that you're trying to build, right? Like you've just got the inputs are A and B. I make C, which depends on A, and it's A times 10. I make D, which depends on C, and it's C plus 5, and so on. And the outputs are now just binding unit. Right. And so yeah, so this is my nicer Arrow API, and it really is like equivalent to the usual Arrow API. So we can build. So if you have something, this is a functor that implements the Arrow interface built based on something that's got a node builder API. So if you give me an X that is a node builder API, I can give you back an Arrow, where the Arrow is the kind of alpha node to beta node builder type. And so that's the implementation of the Arrow. You can also implement going the other way. So given an Arrow, you can create a node and a builder such that there is, at the bottom here, an isomorphism between that alpha node, beta node builder T-type and the original Arrow. And this is an isomorphism by the laws of the various interfaces. Right. The implementation of this is, I don't want to go into the details of the implementation of this. It's not particularly tricky. Like basically, you have, like in a camel, you can use extensible variants to make a heterogeneous store. You could do that to implement a very slow version of refs if you liked. Here, instead of that, I use it to implement this kind of heap structure and track the sharing of the various arrows and do the right thing. It's all on GitHub somewhere if you want to read the details. One important point about the isomorphism, like round-tripping through the isomorphism doesn't build any R nodes. It's just using first and second and dup. That means that any dependency structure that was visible in the original computation is still visible in the output, which is very important for getting the things to be the same performance-wise. Right. And then the last bit, ignoring state threads. Right, so the interface is made like noticeably more complicated, or at the very least more complicated looking, by the existence of that K parameter. The K parameter is there to detect a case where you might take a node from one computation and try and use it in another. You might do that using mutable state, or you might do that by using nested calls to compile. But either way, it's a pretty unlikely bug to write, and it's a shame to make your API much nastier just to catch an error that no one really does. And you can catch it dynamically during compile. So it's not like you get to the point where you're trying to run the graph and it's broken. When you try and build the graph itself, you can detect it very easily and just give a dynamic error to the user. So anyway, that means that if you want, you can go for an API that looks more like this, where builder really is just a monad with nothing else in it, and node really is just an applicative, except with builder.t on the map function. And the key difference here is now, so now you get this nicer looking, your computations now look nicer. They really are alpha node to beta node builder. And the kind of trade-off is now your compile function is in fact partial, right? Like you have this exception unbound node that can come out of compile instead of giving you the right thing, which is a trade-off, but I think it's a reasonably sensible one. Right. Okay. And another interesting thing is that some camel libraries were already doing this. So we've seen in an impure language, ordinary functions have access to a mutable heap. And some existing libraries, in particular Jane Street's incremental library, actually give you an applicative interface for manipulating graphs with sharing, which, as discussed, you can't actually do. And the way they're doing that is they're basically doing the same pattern, the node builder API, but they're just using a camel's ambient monad as the builder monad. I think it's nice to make the monad explicit for the same reason that it's nice to make side effects explicit in general. It makes it a little easier to reason about your code and things. But I think it shows, I was surprised. Mostly this just like, I've been confused by incremental for years, and now I am less confused about how incremental works. Right. So in summary, arrows are applicatives with sharing. Heaps also describe sharing, and you can use those facts to represent arrows as an applicative in a monad. Okay, thanks.
Okay, thank you, Leo. Seems we have several questions. So if you have a question, please come up to the mic in the middle.
So you mentioned that with like adding DOP to the arrow interface, you don't actually need R for desugaring. And R is usually like not liked in the arrow interface because it means that you can only express arrows that can embed arbitrary pure computation. So I'm just wondering why even have R in your arrow interface at this point? Like, what does it give you to still have it there instead of just the incremental arrow, instead of the generic arrow?
Well, I mean, you need R for, like, in this graph. Oh, graph was a while ago, apparently. No, I want the nice graph. There we go.
Yeah, but
like,
this is a graph, like this is an incremental, like a capital I incremental graph, right? It's not polymorphic over the choice of arrow. Or it doesn't need to be. Well, it can't be because you have input and output.
I need a way to define these boxes, though. Like, I'm using R to define these boxes.
Yes, but you don't need a way of doing that that would work in every arrow. You just need to be able to do that in incremental, the same way as you can't have input and output nodes in just any arrow, right?
But I want to be able to take any arrow and run it as in a box. Sorry, I don't think I understand your point.
Okay, sorry, but I thought that this example, because it uses input and output, it only works in your arrow, not like in the incremental arrow, not just any old implementation of the arrow interface, no?
Sorry, after I've applied the R combinator to a function, that is now an incremental arrow, certainly. But it works on any function, and I would like that to keep happening. I don't think I understand your point. I think we should take this offline.
Sure.
Yeah.
So if we go back to the summary slide, please.
Oh, yeah, sure.
So,
Oh,
so
I went too far.
Arrows are
we go.
applicatives with sharing. So I suppose what you are actually saying is that OCaml arrows are OCaml applicatives with sharing, because in Haskell everything is shared, so this issue won't arise.
No,
right?
No. The sharing is still inherent. Like, if I put output nodes and then share to them, like, it would be semantically different whether you shared the output nodes or not. The input nodes as well. Like, it's not just that side effects are being shared. Like, an arrow defines a notion of side effect. Like, it is about representing an effectful computation, and sharing affects those side effects. Like, performing a side effect and performing it twice inside an arrow are different things.
Yes.
And like, the sharing is about those side effects. It's got nothing to do with a camel specific.
Because you see, what happens is that when you go back to that code that the example with x times 5 and x plus 2 and all that, right? What Haskell does is that it lifts that let, to the top.
Sure, but that won't change the outcome.
But that's you get sharing then.
No, you're not sharing. You're just sharing the definite. Like that let was already lifted. Like, the camel code had lifted the let already. Like, that doesn't. Yes, I think it's a fundamental misunderstanding about what's going on. Like, you have a computation, right? Your arrow is a representing computation. It's a description of the computation that you're going to construct. If you put it in twice, it's going to build the. It's going to do the, like, if you have.
Yeah, if you do it
if I let bind right, if I let bind right in, like, a writer monad, and then use that twice, it will write twice. It will not write one time.
Yes.
That's what I'm saying. That's the sharing. Sharing, the fact that you shared the graph that says that the instructions that say do a write doesn't give you sharing of the actual computation.
If possible, I would. Could we talk? I mean, if I could ask for your slides. I believe that you don't have an abstract or paper submitted for the proceedings, right? Well, there are no proceedings at HOPE. Is there a slide that I could perhaps?
There's, like, an abstract somewhere, and, like, there's a library. That's about all I'm going to write about this. So you can read those, or you can talk to me.
Okay.
Hi. I think I want to complain about the ergonomics of what you did.
Wait, you want to complain about the new ergonomics?
I mean, what you did.
That's reasonable, but
you replaced the declarative description of the sharing by an imperative procedure of its construction, right?
That is one way of looking at it, but I'm not sure that it's a particularly.
I mean, other situations where this has occurred is, so for example, TensorFlow also has a computation graph with sharing, right? And it used to be that you had to write the procedure of its construction, and people kind of got bored with that and replaced it with a source code transformation that would recover that from the regular Python program. Is that similar to what you did?
I don't
sort
agree
of
with that
just the other way around?
characterization. I don't think that that is really, like, I mean, just like, it's not particularly procedural so much as it's still
I know it is.
declarative.
I mean, the notation isn't procedural, but what happens
No, it's not
is
just the
procedural,
notation.
right?
Like the actual thing is not particularly procedural. Like the order in which I constructed that graph didn't really matter.
It doesn't, right? But you represented it in a formalism, a monad, where order usually does matter.
Yes, but it doesn't in this case. So that's not true of all arrows. Some arrows care about the order.
Yeah.
But this
So
arrow
another way to
doesn't
look
care
at
about the
this
order.
might be there's Colin's work on compiling with categories. So arrows form a category, and his transformation recovers the sharing
Yeah,
from
but
the
this
original.
is just like a really easy library to implement that doesn't require you to like change your compiler.
yeah,
like
I know,
you can
but
change it if you add syntax for arrows, you can just add syntax for arrows and do it that way.
I'm just saying that in other contexts, right, people have found it worthwhile to add a transformation that would recover this from the declarative.
I don't think I meaningfully see the difference between that transformation and the compile function.
Yeah, I disagree. Okay.
So I'd like to ask you some advice. Mike's complaining about your ergonomics. I want to praise you for your ergonomics. So the advice is this. So in GHC, we've got an arrows library with this sort of API that you described, and a whole pile of special purpose syntax to make arrows more palatable to program with.
Yep.
And that syntax desugars into calls to those things that do a lot of tupling and untupling at runtime.
Yep.
And you seem to have somehow, I can't quite make out, done an end run around all of that.
Yes.
And built a different API that you claim is exactly equally expressive, and
Yes.
that is not only requires less compiler support, but maybe is runtime more efficient and easier to write. That sounds like
it
a
is,
straight
yes.
win.
It
so
is.
is your story, look, you Haskell guys, just throw away those arrows thing, and
Yes.
just use this API for everything that you would, your Yamper should do this. Is that,
Yeah,
is that
definitely.
kind of your story?
That would be that is my
So I'm
opinion.
not
at
overstating
least.
it. No?
I don't think so. It's
Well, I think you should write the
we were
paper.
about to build the like PPX, the preprocessor that would have been the I can't remember what they call the notation for arrows now. I've lost it. It's gone on my
Yeah, the sort of
proc notation or whatever.
oh,
Yeah.
yes, that's
we're,
right.
we're about to build that, and then we made this instead. Like as in it was a big win.
But there's a lot of tupling and untupling that you're not doing.
Yeah, we're not doing that. No, you just build the graph straight away. Like why make a
Yeah,
bunch
it's
of
very
tuples and then like
mysterious.
decode it back into a graph? Just
Okay,
build the graph
I think you should write the
directly.
paper. So you seem to have somehow
so
done
much time.
something very, that gets you a long way without very much effort on a subject, on a topic that people have worked quite hard on. I think that's brilliant. Just write the paper, please.
All right. And Stephen?
So that was really cool. There's an extra bit of state as well as sharing that some arrows care about, and I couldn't quite see where it was hiding.
So they care about the order a bit.
Yeah, exactly. So
but
if
right. So the order is hiding in the monad, right? The builder monad gives you a strict, because really they're not quite just graphs arrows. They're graphs with like a topological ordering on them, kind of like embedded. And the builder monad is giving you that ordering.
Right. So an example is if I use like first F and second G. So I'm doing F on one half the input and G on the other half the input. Then in arrows, first F, then second G is different from second G, then
Yes,
first
and
F.
so this isn't true of the incremental one, which obviously doesn't care about the ordering. But if you swapped C and D, the lines with C and D on it, that would be the same as that's now doing first of one and then second of the other.
Right.
See what I
Okay.
mean? Like that's the yeah.
So and the order that the builder builds them in definitely corresponds to the order that they're hooked together. I can't.
The
But
order
okay,
of the-
sorry, that's where the ordering is hiding.
Yes, that's where the order is hiding. I think it's probably left to right. I'd have to go and look at it again. I did this
Sure.
ages ago.
Thanks.
Okay, thank you, Leo, and thank you for all the questions.